Hi, my name is Jimin Lee from KGSEA Math Circle, and I'm going to give a brief presentation about BFS and DFS search algorithms. Before we go into the algorithm itself, we'll go through what graphs are in a computer science context first, and then a very brief summary of queues and stacks to understand the algorithms later on. Also, please keep in mind that for this presentation, we'll focus more on the algorithm aspect of DFS and BFS rather than the coding aspect, though some codes will also be discussed. Graphs are an abstract data types that are defined as a collection of nodes, also called vertices and edges. Nodes are a fundamental unit of the graph that typically represents an object, and edges are the connections between the two nodes. In this image, you can see that a graph is made up of multiple nodes named A, B, C, D, and E, with edges connecting them. Stacks and queues are commonly used linear data types for storing data or elements sequentially. Stack uses the first in, first out approach for accessing elements, while queue uses the first in, last out approach. These two data structures will be used in BFS and DFS as a way to remember which node to traverse later on. Now, moving on to the true graph traversal algorithms. DFS and BFS are both graph traversal algorithms that traverse or search within a graph. Their common uses include pathfinding from one node to another or finding connected components within a graph. From those two, DFS, or depth-first search, is a graph traversal algorithm that prioritizes moving deeper into a path before backtracking. Its main algorithm can be represented by these three steps: starting at a root or a starting node, then traveling down a branch until it reaches a dead end. This is usually done with the help of a stack, and then backtracking to find another path. These steps are greatly simplified and may be difficult to grasp with a simple text. So let's visualize this process by doing a step-by-step DFS traversal in a simple graph with 5 nodes. In DFS, you first need an array to store the visited node, as well as a stack to store which node to traverse next. Then, you will be selecting a starting node to begin the traversal. In this case, let's choose an arbitrary node A. As A is then visited, it will be added to the array visited. To continue the traversal, you then add the adjacent two nodes B and C onto the stack. After this, you move on to the node that is placed at the top of the stack, which is C. Then pop it from the stack and mark it in the visited array. To go deeper, we will then identify the adjacent nodes to C that have not been discovered yet, which are D and E. Then we repeat the process by moving into the node at the top of the stack. Visit node E, pop it from the stack, and add it to visited. Since all nodes adjacent to E are already visited or are in the stack, you don't need to add any more nodes onto the stack. Then you repeat the process, moving on to node D, and then onto node B. At this point, the stack is empty, indicating that there are no nodes left to traverse. Then we finally traverse the graph in the order of A, C, E, D, and B using the depth-first search algorithm. This Python 3 code demonstrates an iterative implementation of the depth-first search DFS, which was what we have done just now. It begins by initializing a visited array to keep track of nodes that have already been explored, and a stack containing the starting node. The algorithm then enters a loop that continues as long as there are nodes left in the stack. At each iteration, the top node, the most recently added, is popped from the stack, and if this node hasn't been visited, it is marked as visited by adding it to the visited array. The algorithm then examines all neighbors of the current node in the graph. For each neighbor that hasn't yet been discovered, it is added to a stack for future exploration. This ensures the traversal explores one path as deeply as possible before backtracking, which is a key property of DFS. Now that we've seen the traversal process of DFS, let's move on to BFS. BFS, or breadth-first search, is a graph traversal algorithm that prioritizes fully traversing through all nodes of a certain depth before moving on to the next depth. The three main steps of a BFS algorithm are starting at a root or a starting node similar to DFS, then exploring all neighbors of the current depth, and then moving deeper when all nodes of the same distance from the starting nodes are traversed, or in other words, when a particular depth is fully traversed. Like we did for DFS, let's also do a step-by-step traversal for BFS as well. For BFS, instead of using a stack to determine which nodes to traverse next, you'll be using a queue to store the nodes. So you'll still need an array to store all visited nodes, which will be named visited, and a queue to store adjacent nodes that will be traveled next. Same as DFS, you'll be selecting a starting node to begin the traversal. In this case, let's select an arbitrary node A. As A is then visited, it will be added to the array visited. To continue the traversal, you will then need to add the adjacent node B and C into the queue. This is where the clear difference between the two algorithms are shown. Since we're using a queue to store the nodes, we move to the node that is at the beginning of the queue, which is B. Then we'll repeat the usual process by putting B into the visited array and pushing the adjacent and undiscovered node D into the queue. Next on the queue is node C. Just like how we did for node B, it is also put into the visited array and then popped from the queue. At this point, all node adjacent to node C has been traversed, and now we'll be moving on to nodes that are adjacent to node A have been traversed, and now we'll be moving onto the nodes that are adjacent to an adjacent node of A, which is node D. As D is at the very beginning of the queue, we'll traverse next onto node D. As we did for other nodes, add it to the visited array, pop D in the queue, and at this point, as there are no need to add adjacent nodes to the queue, as all nodes are either visited or already in the queue. Next on the queue and last on all of the nodes is node E. As E is then removed from the stack, leaving the stack empty. With the empty stack indicating that there are no nodes left to travel to, the traversal will then terminate. Then we finally traverse the graph in the order A, B, C, D, E by going layer by layer starting from node A. This Python 3 code demonstrates the iterative implementation of breadth-first search. It starts by initializing a visited array to track nodes that have been already explored and a queue implemented by using Python's deque with the starting node. The algorithm runs a loop as long as there are nodes in the queue. And at each iteration, the node at the front of the queue is dequeued for processing. If this node hasn't been visited, then it is added to the visited array. Then the algorithm examines all neighbors of the current nodes in the graph. For each neighbor that hasn't been visited, it is added to the queue, ensuring that all nodes are explored in the order of distance from the starting node. This layer-by-layer traversal is a characteristic of BFS and makes it particularly effective for finding the shortest path for exploring shallow graphs. Now let's summarize the key differences between DFS and BFS. First is the order of traversal. DFS, or depth-first search, explores a graph by going as deep as possible along one path before backtracking to explore the other paths. In contrast, BFS, or breadth-first search, works layer by layer, exploring all nodes at a particular depth before moving on to the next level. In our example, DFS traversed the graph in order A, C, E, D, B, while BFS traversed it as A, B, C, D, E. Another key difference is the data structures used. DFS relies on a stack to keep track of the nodes to be visited later, allowing it to backtrack when it reaches the end. BFS, on the other hand, uses a different data structures to maintain the breadth-first order, ensuring that nodes at the current depth are processed before moving deeper. Lastly, efficiency and common cases where these are used. DFS tends to be more efficient when the target node is far away, as it dives deep into path quickly. BFS, however, is more effective in finding the shortest path in unweighted graphs or when the graph is relatively shallow. To summarize, both algorithms are useful in different scenarios, and understanding their strengths helps in selecting the right one for specific graph problems. Lastly, to give a brief recap of the presentation, we learned about the two graph traversal algorithms, depth first search DFS and breadth first search BFS. The former uses stacks to traverse to the deepest possible levels before backtracking, while the latter uses queues to traverse through each level from the starting node. With this given information, some possible extensions will be modifications of DFS-BFS algorithms for applications in different contexts or problems, using DFS-BFS for more complex graphs, implementing these two algorithms through recursion instead of iteration, and other pathfinding algorithms such as A** and UCS. This is the end of my presentation. Thank you.